Boom. Right-hand sum. If we have this interval, an x sub 0, an x sub 1, and an x sub 2. If you're going to create rectangles within these given intervals, I'm going to create two rectangles, and I'm going to do a right-hand sum. At which point do I evaluate the first height? I go to my interval, and I find the value on the right-hand side. So where do I calculate the first height? X sub 1. So what we will do is we take f of x sub 1 plus f of x sub 2, and we'll end up multiplying those by whatever the width of the rectangle is. And that's how we'll create a right-hand rectangle sum, correct? That's what we've been doing past 2 days here. Now we're going to do a left-hand sum. Same type of curve. I mark off x sub 0, x sub 1, and x sub 2. At which x value will I evaluate my first height now? X sub 0. You notice in one of these situations that you have an overestimation, and another one you have an underestimation. So you will have f of x sub 0 plus f of x sub 1. Pause and look at the notation reflect. Do you understand the difference between those two? If you have any confusion between why we're using x sub 1, x sub 2, and then x sub 0 and x sub 1, you have to ask now, or you'll be lost the rest of the day. Okay, midpoint. Anybody want to take a guess how I evaluate a midpoint sum? Meet in the middle of the interval. So halfway between x sub 0 and x sub 1 would be right there. So that is the height at which I will create my rectangle. Again, right in the middle between x sub 1 and x sub 2. Somebody tell me something interesting about a midpoint evaluation. Yes, you guys said something that's very accurate, but something that's also a little bit inaccurate. First of all, you talked about an overestimate and an underestimate that will somewhat cancel each other out. The key word is somewhat. It is not a pure average of the right hand and the left hand. Because it is a curve, you might end up with more of an underestimation here than you do have an overestimation there. So it's better than the right hand or the left hand, correct? Question is, how do we calculate that? This is a little bit more complicated. We take f of, do I do x sub 0? Do I do x sub 1? Okay, tell me more about half of it. Add it together, divide by 2. X sub 0 plus x sub 1 divided by 2. That is going to be the midpoint of those x values. Plus f of x sub 1 plus x sub 2 divided by 2. You can see you need to find the midpoint of the x values and then evaluate the height there. The last one looks like it's going to be most confusing. It's actually the easiest, and it's my favorite. The trapezoidal sum is awesome. If we have a curve, x of 0, x of 1, x of 2, and they want to be able to evaluate the trapezoidal sum, here's what happens, and here's the conceptual piece that you need to keep in your brain. My right-hand sum, or I'm sorry, left-hand sum, looks like the red, correct? My right-hand sum looks like the blue, correct? What I will do is I will use those figures to create a trapezoid. A trapezoid is how many sides? And two of the sides are parallel. I have a green side with a green side that is parallel. Here's one base, and then there's my other. See my trapezoid? I have a side, a bottom, here's my top. Can somebody tell me by looking at the red and the blue how we would generate the trapezoidal sum? Close, very close. Is the blue an overestimate or an underestimate? Is the red a blue underestimate or over? Under. How does the green compare to the bowl? It's the average of it, right? It's the average of the over and the under. So it is the left hand sum plus the right hand sum divided by 2. So if you've computed the left hand and the right hand, you simply need to average them, and that will give you a trapezoidal sum, which is generally very accurate. See that? So think back when we were doing our work in class, and you guys were, working to try to get a candy bar. You're trying to find that area. This would have been a really good method, right? Okay, really good method right there. So, all right, here we go. We're going to do 3 examples, actually 4. One will be table-based, second will be rule-based, third will be graphical, the fourth one will be using technology. I will get more complicated as we progress. It says use the following table to determine the approximate area bounded beneath the function over the interval -2 to 6. This notation right here means I want to find the right-hand sum using 4 rectangles. What is the width of my entire interval? I have a width of 8 for the entire interval. So if I'm going to create 4 rectangles, what's the width of each rectangle? 2. So my first rectangle will be from -2 to 0. Second rectangle from 0 to 2. Third from 2 to 4. And fourth from 4 to 6. We don't see the picture, but we need to think about conceptually what we're doing. Remember that we take the width times the sum of the heights. The width is 2. We're going to multiply it by the sum of the heights. That's why we calculated it, as opposed to multiplying every height by the width. We just write it like that using our distribution property. So if I'm doing a right-hand sum, what is the x value at which I evaluate my first rectangle height? 0. I look at this interval, and I move to the right-hand side of it. I evaluate the height at 0, and it is 1. Second spot, I evaluate my height. And I get third spot, and I get fourth spot, and and I get 6. Add them up. I got 7 and 7 is 14 plus 18. 8 is 22 times 2 is, I got 44. What do you guys got? It's great to look at a table because it helps you understand what we're going to do later on. How will the left-hand sum be different from this right-hand sum? Okay, I start with the left, so what number will I add? The 5. What number will I take off? The 6. You see that? So I have the same business, 2 times, I got 5 plus 1 plus 7 plus 8, and I take off the 6. 15, 20, 21 times 2 is 42. Thank you, Haley. You're super smart. Well, thank you, Mr. You're welcome. All right, so now we look at the midpoint sum. So what I have to do is I have to look at my x values, which are negative 2 and 0, and I have to find the average. What's the average between negative 2 and 0? Negative 1. So my width stays the same. My width is 2 times, what's the height at negative 1? Plus, what's halfway between 0 and 2? And I get 5. Halfway between 2 and 4. And I get halfway between 4 and 6. And I get 5. I got 10, and 10 is 20. 36 times 2 is 72. A trapezoidal, again, sounds most difficult, but it's quite simple. All I'll do is I'll take the average of what? Right hand, left hand. You can tell it's going to be 43. So 44 plus 42 divided by 2, and I get 43. Done and done. How are we doing so far, folks? All right, flip it over. Approximate the area bounded between the curve negative x squared plus 16, the x-axis, and the y-axis in quadrant 1. What's different about this problem compared to the one we just did? Okay, it doesn't give us the y values, but we do have a function rule. What else do we have? Not have. Doesn't give us an interval. Very good. So the graph of negative x squared plus 16 looks like this. It's up at 16 units right here, okay? But and it starts at 0 here because it says we're in the first quadrant. But where would be the spot where I would finish evaluating the area? We're across the x-axis right here. What spot is that? The y value is 0. What's the x value? 4. How'd you get 4? Yeah, you take 0 and set equal to negative x squared plus 16. Factor out the negative. So this has x-intercepts of negative 4 and positive 4. We're looking for the positive 4. So our interval is from 0 to 4. Those are things you need to be able to think through if you're given a problem like this. So interval is from 0 to 4. You could, but it states here that we just want quadrant 1. So because of our restrictions that were placed on the problem originally. Okay, what is the width of our interval? 4. How many rectangles are we dividing into? 5. So what would be the width of each rectangle? 4/5. Okay, I was waiting for the angry face. Thank you. Saw it. It's there. Got it done with. All right. Now you're smiling again. So 0.8 is going to be the width of each interval. So as we look at the right-hand sum, the right-hand sum will be 0.8 times the sum of the heights. Now, if you have to create a drawing, go ahead and create a drawing. Okay? So if I have 0.8, and then I go by 0.8 again, I'll get 1.6, 2.4, 3.2. You either need to draw this or picture it in your head. What is the first x value at which you evaluate your height? 0.8. have f of 0.8 plus f of 1.6 plus f of 0.4 plus f of plus f of 4. We're going to evaluate that in a second, but before we do, how would the left-hand sum be different? Where would I start? Start at 0 and I would end at 3.2. So I just wrote exchanging f of 0 for f of 4. We just exchanged the beginning and the end. Otherwise, it's the same. For this problem, I would choose to go to my table. Anybody use their table for their worksheet yesterday? Okay, so let's use our calculator for that purpose. Y equals, I type in negative x squared plus 16. And I'm going to go to my table. And I need to change it to ask. So my calculator resets all the time. So we go in a table, and I'm going to type in all these values, 0, 0.8, 1.6, 2.4, 2.2, 4. So we basically now have our very first problem, don't we? I mean, this is your table values. It's now like we're looking at the first problem we did, right? So you can always bring it back to table values. Okay, 0.8 times 15.36 plus 13.44 10.24 5.6 here. 0.8 times, looks like we start with 16. Anybody do the calculation? If not, I'll do it. Either one. When you got a question? Looks like for 2.4, get 10.2. 35.84. Anybody on the second one? Okay. Consider the drawing. Is the right-hand sum an underestimate or an overestimate? This time the right hand is an underestimate. The left hand would be an overestimate. So let's do the one we can do really quickly. That's to find the trapezoidal sum. How do you find the trapezoidal sum? 35.84 plus 48.64 divided by 2. Anybody who has a computation? Very good. Now I'll try an example that's just a little bit more difficult. We'll look at the midpoint sum. The width of the rectangles for midpoint sum does not change. It's still always going to be 0.8 because you're still dividing it into 5 rectangles. The question now is, what do we do regarding the heights? So let's evaluate the heights. We'll do that when we get back. Go have a great lunch. And go. We're at midpoint sum. Okay, midpoint sum is a little bit more challenging. So try to follow along here. If you don't, you have to ask questions immediately. This is the point of confusion that people had. Midpoint sum. Notice how I list these. I have 0.8, 1.2, 2.4, 3.2, and 4. Oh, and 0. Okay, those were all the spots that I used to evaluate heights over the course of the interval from 0 to 4. The question is, if I'm doing the midpoint evaluation, where's the first spot that I evaluate the height? 0.4. Then what? It's 1.8. Folks, watch. Look here. This is so important you see this, otherwise you'll be confused when you do your assignment. The midpoint is the average of the two values, right? And the average of 0.8 and 1.2. Oh wait, I'm sorry. I'm sorry. You're absolutely right. I made a mistake. I just wrote them down. 0.8 and 1.6. Okay, sorry about that. So 1.2 is absolutely correct. Okay, sorry about that. So we have these two, and then the average between 0.8 and 1.6, we would add them, get 2.4 divided by 2 to get 1.2. Now, you don't have to do that every time, because look at what the increase is. What's the increase between 0.4 and 1.2? 0.8. Why is it an increase of 0.8? Because that's the width of our rectangles. So it'll be f of 2, f of 2.8, and f of 3.6. Notice how far from the end is 3.6? 0.4. See that? Half of our distance, half of our width. Yes, perfect. All right, so let's evaluate that. Put my calculator on. Oh, please turn. Okay. You guys are probably able to do this quicker than I can. Y equals negative x squared plus 16. And we have, that's my y equals, and then I go to table, I have to go to table set, ask, table values at 0.4, 1.2, 2, 2.8, 3.6. Those are my 5 values. 0.8 times the sum of those, 15.84. It's 14.56, 12, 8.16, 3.04. 15.84. 42.88. What do you think? See how we set it up? So we did midpoint, I'm sorry, left hand, right hand, midpoint, trapezoidal sums. We did one using a table. We did one using our function rule. And now we look at one graphically, and then we're going to do a technology piece here. So look at example 3. Use the following graph to evaluate the following sums over the interval 0 to 120. I want right hand of 4, left hand of 4, midpoint of 4, and trapezoidal of 4. What is the length of my interval? Each width will be 30. The entire width is 120. Divided into 4 parts will be 30. So I will draw the rectangles here. 30, 60, 90, 120. So we have 4 times the sum of what's the height evaluated at 30? 40. Plus, oh, I'm sorry. The width is not 4, the width is 30. Times 40 plus 80, 20, 100. So it's 30 times, let's see, I have 100, 100 is 200, 240. 7,200. Left hand of 4. I'll draw that in red. So my red rectangles represent the left-hand sum. I still have 30 times. How will it change from the right hand? What will I add on? What will I get rid of? I'll add on 0 and get rid of 100. So 0 plus 40 plus 80 plus 20. 30 times 140, 5,200. Midpoint. At what spot do I evaluate the height for this midpoint of this rectangle? 15, so it looks like this will be my first rectangle. I evaluate 45. I evaluate at 75. Evaluate at 105. Looks like that should hopefully be a much better estimation. So I have 30 times. What's your first height? 10. 60. How about your third height? 50 and 60. So 30 times, let's see, 120 plus 70 is 190. And that makes 5,700. What do I do for the trapezoidal? I'm sorry, folks. I wrote 5,200 here. It's 4,200. 3 times 14 is 52, it's 42. Okay, trapezoidal sum would be 7,200 plus 4,200. We're going to divide by 2, and you get 5,700. What do you notice? What's the same? The trapezoidal and the midpoint. I want you to focus on that for just a second. Watch me draw the trapezoidal sum. I have a left-handed rectangle in red. I have a right-handed rectangle in green. In black, no, in magenta, I will draw the trapezoidal. What do you notice about the trapezoidal here? It's the exact area. Why? That's because it's linear, so that will do a good job. Okay. It makes shapes that we know how to find the area of, right? Like if I ask you to find the exact area there, you could cut it up into rectangles and triangles and be able to find that area. So, okay, last example, flip it over. The graph of sine of x. We want to find the area bounded between the curve sine of x and the x-axis over the interval of 0 to pi. What is the period of sine? 2 pi. What is the maximum value? Minimum? Start in the middle, top or bottom? Middle. We're not looking at the second half of the graph, but just the first half, where it's above the x-axis. We will find that area. Since I would divide it up into how many triangles? Or rectangles? 100. That might take a long time to do by hand, right? So we need our calculators. Now we're going to input something into our calculators. We're namely going to input this. The width times the sum of the heights. In order to input that in our calculator, here's what we do. We take the width times, we use an operation called sum, and then do you notice that when we sum up your heights, there's a pattern as to what we choose? Like we increase by a certain amount every time, right? 0.8, 1.6, 2.4. So that creates what we call a sequence. Once we decide we evaluate the height at, say, 0.8 or 1.6, what do we do with that 0.8 and that 1.6? We plug it into our function. So we need to identify our function. Your calculator wants to know the variable that it should plug it in for. What variable do we plug it in for? X. It wants to know the first spot at which we evaluate the function height. What else do you think it wants to know? The last spot evaluates the function height. It wants to know one more thing. How much we increase each interval by. So that would just be, again, your width. Let's start with the right-hand sum. So we will do right hand of 100 rectangles. What is the length of the interval? Pi. If we divide it up into 100 pieces, what's the width of each? Pi over 100 times the sum of the sequence of, what's our function? Sin of x. What variable would we like to plug it in for? X. If I'm doing a right-hand sum, what's the first spot that I evaluate the height at? Pi over 100. I would start at 0 and add on that width of pi over 100. What would be the last spot right before we get to the end? 99 pi over 100. So I added on a width and I backed off a width. So you see that you can see your first and your last interval pieces, right? Where you draw your rectangles. So let's use those for these problems. Okay? So I have sine of x, my first spot is pi over 100. If I'm doing the right side, what's the last spot I do the height? The right side of this interval is pi. And what is the increase of each interval? Pi over 100. Your calculator is going to want to put a parenthesis around x. That's just what it does. So it's like I want to try to make sure I see 1, 2, 3. Oh, looks like I take that. Just going to make sure I write it down correctly, and then I'm going to go to my calculator and I'm going to type this in. Oh my gosh, I can't believe it. 3 times I've had to reset this calculator. Okay, our width, pi divided by 100. Sum, I choose to navigate through catalog. Second, 0, or catalog. I want to to get to the s's. So I can press S, but SU for sum is close to the T's. So if I press T, I'm at tangent, and I back off to sum. Then sequence, same thing. I go to my catalog, I press S, and I go down to get sequence. You want the sequence that has the parenthesis. Now what? Sign of X, make sure that you close your parenthesis. What do you notice I have written after the sign of X? A comma. Then pi, then pi over 100. So I have two parentheses to close it. Take a while for your calculator to compute this. Awesome. There we go. 1.99984. We'll carry out to 5 for this one. You guys tell me. What do you think the exact area bounded underneath this curve is? It's 2. As we increase these rectangles from 100 to 1,000 to a million, we get really close to the number 2. And that's what we're going to do on Tuesday. We're going to let this number of rectangles go to infinity, and then we won't use our calculator. We're going to do it by hand. And we'll get 2. It'll be awesome. Really can't wait. All right. So now I want to do the left hand of 100 as well. And so I'm going to type in basically the same thing, pi over 100 times the sum of the sequence of sine of x. My variable is x. But if it's the left hand, where's my starting point? 0. What's my ending point? 99 pi over 100. What's my width of each one? Pi over 100. Now, because I'm super smart, I can take my calculator and I can go second entry, and it'll bring up everything I just plugged in. That way I could go back here and just change a few pieces. 0, comma, 99 pi divided by 100, comma, pi divided by 100. So it saves me a little bit of time. .99885. How would you do trapezoidal sum? Add them together, divide by 2, 1.998984 plus 1.99885. Divide that by 2. $1.999345. And I'll tell you on the test how far you should round it out to. What's the last one we have to do? The midpoint. I have pi over 100 times the sum of the sequence of sine of x What do I put after sine of x? x. All I have to figure out is my beginning and my end. Now here's where you got to think about it. Look at what I drew. What's halfway between 0 and pi over 100? Pi over 200. And then if you back off from this last spot, pi over 200, what would you get? 199 pi over 200. And if you type that in, that will give you your midpoint, which is exactly where we ran out of time for the last class. I have your worksheet. You have an assignment, which is the worksheet I give to you. You also, remember, do not have school on Monday. So you should be doing your math, everybody, because on Tuesday, infinite number of rectangles, get your seatbelt. This could be a big day. Darn right.